Alright, let's begin with the display of our project. This project is called sliding mode PID control of a heater and cooler plant. So if we look at the project, these two are our PID plus SMC, which is proportional integral derivative plus sliding mode controllers. This is our subsystem for our heating and cooling plant. This is our set temperature and this is our ambient temperature. Now, if you might look, our ambient temperature is not a simple constant. We have added some disturbance. How we've done that? We've taken a 10 hertz triangle wave. Let me open the, yeah, you see 10 hertz triangle wave, and we've added it with a constant one. The reason we have done that is because we don't want any negative values. We multiply that by a disturbance gain. For now, I've kept it 3 because that's a reasonable amount. And our actual ambient temperature is around 27 degrees centigrade, but obviously our real life or real world temperatures fluctuate in the micro um, degree Celsius sense. So that's how it happens. Now our set temperature is compared with our ambient temperature, and if our set temperature is higher than our ambient temperature, then this relational operator block will output a value 1, which will turn on this heater switch. When it turns on this heater switch, it will turn on our PID plus SMC heating control block. So let's actually look into that. So this is the controller architecture, which is a combination of two types of control. One is a PID control and one is a SMC control. PID's control is simply proportional integral derivative. It is an error amplifier which generates a proportional signal due to feedback. And as the error reduces, the signal also reduces. But there is an issue. A lot of PID controllers, they are simple to implement, but they are very easy to overshoot. By overshoot, I mean they will go beyond our set temperature value, and that could damage certain components. And even if you have properly tuned your PID controller, environmental issues, environmental changes, device properties changes will always never accurately give you 100% good results. In this case, another type of control strategy called sliding mode control, which is basically defining a sliding surface on which the system is going to act on. Now, that type of controller is a very good robust controller, but there comes a downside with it. It does something known as chattering, which is very high frequency switching, which can damage a lot of our MOSFET switches or relays. So here we have gotten the best of both worlds. We've gotten the simplicity of our PID controller and the robustness of our sliding mode controller. We have implemented our PID controller by simply having an error block which takes our set temperature and subtracts our output temperature. So that's giving us a feedback loop. When that gives us a feedback loop, an error is generated. That error goes through a proportional gain of 1. Now, the way I calculated these gains is by simply taking our first order equations. Yes, our heating and cooling models are first order equations, and substituting our PID output u of t in them. Once I substituted that, I had to solve the second order differential equation, and I kept my damping ratio as 0.5 and my settling time as around 2 to 3 seconds. Once I calculated those gains for kpk and kd, I assumed kd as 1 for both heating and cooling. I will explain to you why later. But for now, from my calculations, I got kp as a whole number of 1 and ki as almost as a 0.48. I could also keep it 0.5. It won't make a difference. Now comes the interesting part. How did we apply a sliding mode controller? You see, a sliding mode controller depends on 3 variables. S, which is a sliding surface. Now that sliding surface is defined by 2 other variables, which is known as K, which is a sliding surface gain, and second, which is phi, which is simply our error multiplier. Now, why do we require an error multiplier? You see, the way we are applying sliding mode control here is via dynamic saturation. A dynamic saturation allows our upper and lower limits. We are basically saturating. We are applying limits to the input error. When we are simply multiplying this input error by 250, no matter what happens, eventually that error is going to reduce, and as soon as that error gets to 0, even if you multiply it with 250, the limits are going to be so small that the output is going to be clamped, and this clamping action is exactly what gives us our sliding surface. Now this is another gain which is very important. K, our sliding surface gain is very important because this sliding surface allows us to keep the same rise time and settling time every single time. What do I mean by that? No matter how much I change the input temperature or the ambient temperature, we are going to get very consistent settling and rise times. We get that because this gain is what regulates and takes this input towards our saturation, towards the sliding surface, which is S in our case. So here my upper and lower limits are plus 250 minus 250 multiplied by this error. Now you might be noticing I've used a filtered derivative here. The reason why I've used a filtered derivative is because PID controllers also suffer from chattering in a very small amount compared to dynamic saturation, but they still do. And applying a filter coefficient of 100, in this case I have kept the time constant as 0.001, which is basically 1 divided by 100, and our sample time to constant time ratio is 100. So this gives us a filter coefficient of 100, which is a very modest and not an exceedingly overkill value. Now that we've gotten the PID plus SMC heating block, we'll also look at the cooling block. It is identically the same. The only difference is that here our upper and lower limits are 250 and minus 2. Okay, it is the same. My bad. Um, Here our KP is different. The reason is because when we model our heating and cooling equations, okay, I will get to that in just a minute. Here our KP is 0.36, our KI is 0.224. Now you might be noticing that that is a much lower gain. The reason is because in this equation, yes, this is our plant equation. The upper equation is our heating equation. The lower equation is our cooling equation. They both use the same ambient temperature, which I described before, and they both have two algebraic loops where the output is basically a derivative of temperature, and one of the terms is the output temperature. So you have to integrate that output temperature in order to actually get the correct output. So there are two algebraic loops here. Now you'll be noticing this is called KH, which is the heating gain, which I've kept as 5. And you'll be seeing KC, which is a cooling gain. Now I've reduced the cooling gain from 5 to 3.5. The reason is because most air conditioners in our homes today are 3 stars, and most 3-star ACs have a COP or coefficient of performance of around 3.8 to 3.9. The reason why I've kept 3.5 is because this is a very ideal equation. So we need to lower our expectations in that case. I've kept the time constants as same for both because it's not going to make much of a difference. It is 10 seconds for both of them, and the value is called tau. I've gotten two switches here again, which again either turn on the heating equation or the cooling equation, and eventually the temperature is added. Now you might be wondering, it does not make sense to add the temperature, right? It actually does. The reason is because when the heater switch is on, the cooler switch is going to be off. That means this output is going to be 0. So no matter what happens, if you add 0 to this temperature, it's still going to give you an output temperature. And this is how most HVAC systems work. Heating, ventilation and cooling systems work. They simply have their controller architecture, have one switch turned on and one switch turned off, and add both of the outputs. That really helps with the simplicity of the architecture, and also this is a very reliable method of applying it. So now that we know that, yeah, we are observing 4 things here. We can observe 2 other things as well, but this is not a very important, not very mandatory to observe. The very first thing is the heater control output. Then the second is the cooler control output. The third is the ambient temperature disturbance. How much disturbance are we getting? And the fourth is the actual temperature output. So here we can see we'll first start off with some heating. So let's take it to 100 degrees Celsius. Let's apply it. Now Run. We've ran it, and let me just resize this. Yes. So as we can see, this heater control, it initially begins at 100 degrees Celsius. Why? Because the error difference is 100 and it reduces, then it increases, and then it reduces again, and it eventually settles to a constant value. Sorry, there's some issue with the mouse. Yeah, okay. Then this is our ambient disturbance. As we can see, it goes from 27 degrees Celsius to 33 degrees Celsius. This is a little too extreme. This does not happen in real life climate, but this is to simply show that our controller can still output a very stable 100 degrees Celsius. As you can see, it is behaving as a second order system up until here, but as soon as the error clamped, as you can see, that's what I've been trying to tell you, the error clamped the input. Sorry, one second, I'm just trying to figure this out. Yeah, when the error clamped this input, as you can see, it sort of fell, it sort of started sliding over this surface. That's why it is called sliding mode control of our heater and cooler. So as we can see, the heater part of the section works very well. Now let's do the cooler. So we have to pick any temperature below 27. So let's pick a temperature of, let's say, 14. That seems like a reasonable one. So let's pick a temperature of 14. And let's see what is our output like. As we can see, our temperature output again gets perfectly up to 14. Let me just zoom in a little bit. Yep, pretty much 14. And you would notice that it is, sorry, I am using a mouse pad and unfortunately I'm not able to navigate it so well. So as you can see, the ambient disturbance stays the same, but in this case, our cooling control is not so extreme. You see, we set a very small difference of temperature, so obviously it is going to give a very small output and requires a very small output. Actually, it requires a negative output to sustain this certain temperature. The reason is because our plant model basically behaves where this cooling gain is subtracted from our input temperature, and when that is subtracted, that gives us a cooling effect. So that gives us a first order differential equation. If we were to model this into a second or a third order differential equation, that would be more accurate, more robust, more difficult to control. But this is the simple know-how of how real world systems can be put into mathematical equations and can be controlled in different ways. So now that we've established that a gain of 3 is very easily handleable, let's give it something extremely extreme, like very extreme. Let's give it something like 10. All right, if we give the disturbance gain as 10, our disturbance is massive. In this case, it swings all the way from 27 to 45. That is a ridiculous difference, and it still gives us a very stable output, almost a straight line, just a little bit of oscillations, which is expected. We've watched all of these. Let's just watch these two scopes, which are not mandatory. This simply to verify that the switches are turning on at the correct space. As we can see, these switches, oh, this is simply connected to our output temperature. As you can see, it's simply connected to our output temperature. So these are not really required. But in this case, the cooling switch is on and the heating switch is off. That is what we had to verify. And we've done that. So this is sliding mode PID control of heater and cooler for